Hi all, welcome to my ozone technology course. This will be session 14, which will be on the chemical properties of ozone. It is necessary to know some fundamental properties of ozone so that we would be able to understand its application in some of the many fields. Right, first of all, we have to know what exactly ozone is. Of course, we have already done a bit of information. The ozone is a triatomic oxygen, which has got 3 oxygen molecules or atoms in one molecule. If you look on the diagram on the right, you find that there are 3 oxygen molecules, and each of them are connected by a double bond. We know oxygen has got 4 particular bonds available for combination. Now, when ozone breaks down, what happens is it becomes oxygen, and there is an ozone atom that comes out. And this ozone atom cannot survive on its own because it has to combine with something else to oxidize, and therefore it's highly active and it reacts with anything possible. As I mentioned, because of the very high energy levels of that singular oxygen atom, it will be able to combine with many chemicals and rapidly oxidize chemicals. Ozone itself is a plain blue gas. It's not generally visible if you bottle up ozone and try to have a look at. The power of ozone is able to oxidize, and it's measured by its redox potential of 2.07 volts. We have done the potential charts very many times, and we also note that the oxidizing capacity is 4th after fluorine and hydroxyl radical. Ozone is denser than oxygen, obviously because oxygen has got 2 atoms and ozone has got 3 atoms. Oxygen decomposes in water with a half-life of 20 minutes. That is, of course, temperature dependent. Half-life means 50% of the gas decomposes within 20 minutes. And a further 50% of the remainder in the second 20 minutes, and so on. In the air, the decomposition is much slower, and it takes 1 to 3 days. That's also dependent on the temperature and the humidity. Of course, ozone, when it's released into the air, is dispersed by the movement of wind. This ozone is also polar, and therefore it attracts the polar chemicals. It's more soluble in water than oxygen because water has got a bit more polarity and oxygen itself has less polarity compared to ozone. And therefore, for the same reason, ozone is more soluble in salt solutions and some organic liquids. In solution, the redox potential of water or salt water increases as it dissolves more ozone. This makes the ozone very active in the water as an oxidizing agent and used in many applications. Just like any gas, solubility reduces as temperature increases. This chart represents the ozone solubility in water with respect to the pressure of water pressure. You will notice that at about atmospheric pressure, you have about 30 milligrams per liter solubility, and it increases as the pressure is increased, and at about 20 psi, the solubility is about 60 milligrams per liter, and about 30 psi is 80 milligrams per liter. So when we manufacture oxygen or ozone, generally the pressure is around, the gas pressure is about 20 psi, and we could increase it to 30 psi and allow it to dissolve in the water. But we are limited by the ability of the machine or generator to be able to accept higher pressures. As ozone is a gas, it follows the principles of chemistry with respect to solubility and physics, the phase rule when it comes to solubility of gases. Solubility of ozone in the saline solution, as I did explain to you, is higher than in normal water. Here again, I have to bring the famous charts with respect to the electrochemical potentials. For example, the free radical, we have 2.8. Ozone atom that is nascent ozone as 2.42, and ozone itself is 2.07. Hydrogen peroxide comes further down below ozone. Chlorine dioxide is higher than chlorine gas itself here, which is higher than oxygen. And the liquid chlorine, which is used in the swimming pool, is virtually in the form of HOCl, which has got 0.95 volts. Because of its high reactivity, ozone reacts with very many metals to form metal oxides. Example, with iron it forms iron oxide, with tin it forms tin oxide, with copper it forms copper oxide, heavy metals, oxides like arsenic, lead, etc. So you see that we can use ozone to remove iron, we can remove arsenic, and we can remove lead from the water. And other methods, chemical methods to remove arsenic and lead are pretty cumbersome. And so we take into consideration that ozone is the best gas or best method of treating and removing arsenic and lead. Of course, it can also remove cyanide. You will understand that in mining of gold, cyanide is used to react with the gold, and then they release the cyanide to get back the gold metal. And the cyanide is very toxic and released to the water in the wastewater, and this cyanide kills fish and marine animals. So we can use ozone to try to remove and oxidize off the cyanide. I mentioned that you have the cyanide. Cyanide is converted to carbon dioxide by ozone, cyclic hydrocarbons to straight chain compounds, straight chain hydrocarbons to lower chains. Ozone reacts phenol to straight chain compounds. Soluble heavy metal compounds are oxidized to insoluble oxides and precipitates, includes lead, silver, and arsenic. Soluble of iron is oxidized to insoluble ferric oxide. It denatures proteins, causes soluble proteins to become insoluble precipitate or flocculate. And we did learn in proteins that if any one of the chains of the protein is disturbed, its solubility, its characteristic changes, and the solubility decreases, and it becomes insoluble and most likely like a colloidal solution. Ozone can destroy CFC rather than CFC destroying ozone. Obviously, they are interlinked. Ozone reacts with the CFC to form fluorine and carbon dioxide. The reason why ozone is depleted in the ozone layer is because the CFC goes out onto the ozone layer and the ozone reacts with it, destroys the CFC and gets used up. Note, even though this is known, the industry does not use this method to destroy the CFCs in the earth, but rather allow them to seep slowly into the atmosphere. Ozone also decolonizes and deodorizes. Both color and odor are long chain conjugated carbon-carbon bonds which are broken by ozone. We will be dealing with these in a little bit more detail in the next few slides. We know that fluorine, bromine, chlorine, iodine, all these are part of the halogen group, and they have got very similar reactions with ozone. Ozone will react with hydrogen bromide to form bromine. It will react with bromine to form bromate. It will react with hydrogen iodide to form iodine. It will react with the iodine will react with ozone to form iodate. Ozone, however, will not react with hydrochloric acid or hydrogen chloride or hydrogen fluoride simply because the bonds between the two halogens and hydrogen are too strong. When ozone is subjected to nitrogen dioxide, it forms nitrogen oxide or nitric oxide, and that's how nitrites are oxidized. Hydrogen sulfide is oxidized by ozone to form sulfur dioxide. Sulfur dioxide can be further oxidized to form sulfur trioxide. You will recall that we did study the structure of carbohydrates, fats, and proteins. And in carbohydrates, you have long chain carbon compounds. In proteins, you also have long chain carbon compounds, which include nitrogens, and they may either contain single bonds double bonds or triple bonds. When ozone is subjected to a long chain carbon compound, if it has triple bonds, that bond will be broken into, one of the bonds will be used up and ozone will react and form hydroxyl grouping. If you subject it further to ozone, then it will form another hydroxyl grouping and the double bond is broken up into single bond. The next final stage of oxidizing the single bond to break it up will be difficult, but it can be done if under special circumstances. From here you note that ozone will attack any double or triple bonds, but not necessarily single bonds. But it will react with conjugated bonds. What is a conjugated bond? This particular combination is a conjugated bond. You find that this is a single bond, this is a double bond, this is a single bond, that is a double bond and a single bond. So you find that these bonds are conjugated. In other words, one single, one double, one single, one double, one single, one double, etc. Of course, in between you might have one triple. Whether it is a double bond or a triple bond, ozone will react. However, as I did mention, it's very difficult for ozone to break up the last of the carbon-carbon bonds unless special characteristics are used. For example, we can possibly break the single carbon-carbon link using hydroxyl-free radicals. We will deal particularly with the oxidation of metals by ozone. This will be applicable to many of our ozone treatments. First, the iron oxidation. In our waters, in many of the waters in the reservoir or rivers, there might be quite amount of iron, which will give coloration if we boil it, and it may be unpleasant to taste. For example, presence of iron will provide tea that will be green in color. So in order to remove the iron, all we have to do is pass ozone, and the ferrous iron will immediately deposit as ferric hydroxide, or more or less a brownish reddish precipitate that can be just filtered out. With respect to manganese, quite a number of well waters do have manganese, and these cause coloration to clothes, a brown sort of coloration. So in order to remove the ozone, in order to remove the color of manganese, we pass ozone through the water and the manganese will become precipitate out as manganese hydroxide. Of course, we have to be very careful with respect to further application of ozone because this manganese hydroxide may be converted to permanganate, becomes soluble. So insoluble manganese hydroxide will become soluble permanganate, which is not suitable for us. Ozone can also remove arsenic in the water by oxidizing and getting arsenic oxide, which will become a precipitate, and we should be able to filter it off. For those who are interested, I have provided two references for arsenic removal from wastewater and oxidation of arsenite in groundwater using ozone and oxygen. Next, compared to the other metals, lead, cadmium, copper are also heavy metals, and that also can be removed by passing ozone through the water that contains lead, copper, or cadmium. We must not forget the fact that all these metals can be removed by chemical flocculation, which may be too costly for the community, particularly where millions and millions of gallons or liters are involved. The advantage of ozone is that insoluble oxides from the oxidation of the soluble compounds are quick and less costly and can be applicable for very small applications in the commercial side where they are needing to use water for their manufacture. Thank you for the patience of listening to my session. We have come to the end of the session 14. The next session 15 will be on the principles of application of ozone to liquids. And if you are new to this session, please refer to sessions 1 and 2 on program details and sessions 3 to 13, which is the comprehensive information on the application of ozone. If you like this presentation, please click the like icon and subscribe icon, and you will be notified as soon as the next session is uploaded. Thank you very much and have a pleasant day.